Hello everyone, welcome back to my channel. This is the second video on current electricity, and in this video I'm going to discuss about electrical resistance. Electrical resistance. So what is electrical resistance? Electrical resistance is the property of a material that obstructs the flow of electric current. Okay? Electrical resistance is the property of a material which obstructs the flow of electric current. Electrical resistance is denoted by R. Okay? Suppose there is a conductor and a potential difference is applied across the two ends of the conductor. Because a potential difference V is applied across the two ends of the conductor. Now what happens? The electrons of the conductor gets drifted towards the positive end of the conductor. The free electrons gets drifted towards the positive end of the conductor. Now, as the electrons gets drifted towards the positive end of the conductor, they suffer collision with the positive ions of the conductor. So this opposition, which is offered by the positive ions of the conductor, is known as electrical resistance. Okay. So suppose a potential V is applied across the two ends of the conductor and a current I flows through the conductor. See, battery never offers electrons to the conductor, but they let the electrons in continuous motion. They drive the electrons. So if the electrons move towards the positive end of the conductor, the current will flow in the opposite direction. Current always flows in a direction opposite to the flow of electrons. So if a potential V is applied across the two ends of the conductor, and if a current I flows through this conductor, then the electrical resistance R is given by V upon I. Okay? V upon I. The ratio of the potential difference across the two ends of the conductor to the current flowing through it is known as electrical resistance. Okay. Now, from Ohm's law, we know that Ohm's law says that the potential that is applied across the two ends of the conductor is directly proportional to the current flowing through it. So in that case, V will be equal to Ri. According to Ohm's law, the electrical resistance R here is constant. Only because if R is not constant, then V will not be proportional to I. Only if V is constant, then only if R is constant, then V will be proportional to I. But this is not always valid. This is not always true, because resistance may or may not be always constant. Resistance of a conductor may not be always constant. So this formula may not be applicable. But the formula of the resistance, which is given by V upon I, is always valid. It is always applicable. Alright? Okay? Yes. Now, the SI unit of resistance is ohm, which is given by this symbol ohm. Okay? The SI unit of resistance is ohm. Now, in the first video, on the concept of drift velocity, we derived the formula for drift velocity, which was Vd, drift velocity is equal to E charge of an electron into electric field, okay, upon m times tau. This is how we derived in the first video. This is how we derived the relation for drift velocity of electrons. Now we can manipulate this relation as, see, suppose this is a conductor to a conductor of length L. If a potential V is applied across the two ends of the conductor, then electric field is set up across the conductor, right? Electric field is set up across the conductor. In that case, that electric field E is given by V upon L, where V is the potential that is set up across the two ends of the conductor, and L is the length of the conductor. In that case, your relation Vd becomes charge of an electron, E means V upon L, right? V upon L divided by m times tau, where E is the charge of an electron, V is the potential that is applied across the two ends of the conductor, tau is the average relaxation time, m is the mass of the electron, and here your L is the length of the conductor. So this is the relation that we have derived for the drift velocity in the first part of the video. Yes, so we are recalling that relation. And then we have also studied that the relation between drift velocity and electric current is given by I is equal to NAE Vd, where Vd is the drift velocity of the electron. So using this relation, NAE, what is your Vd? EV tau upon ml. Now in that case, your I becomes equal to NAE into E square V tau upon m times L. Now if we cross multiply this relation, then we have NAE square V tau is equal to I times ml. So this implies V upon I will be equal to ml upon NAE square tau, right? So in that case, your V upon I becomes equal to ml upon n. Area means we can write length into length, so square of the length is square tau. 1L from the numerator, 1L from the denominator can be cancelled out. So we have V upon I is equal to m upon n L E square tau. Okay? Yes. Or we can just keep the relation, in this form. There is no problem. We can just keep the relation in this form. Then V upon I is equal to m times n E square tau into L upon A. Now here your V by I, what is your V by I? V by I, ratio of V to I, V upon I is known as your electrical resistance. The ratio of the potential to the current flowing through it is known as your resistance. The ratio of the potential applied across the two ends of the conductor to the current flowing through it is known as your electrical resistance. So V upon I is known as your electrical resistance, which is equal to M upon N E square tau L by A. Okay? Here, M is the mass of an electron. So mass of an electron is always constant. N means number of electrons per unit volume, which is always constant. Here is the charge of an electron, which is always constant. And tau is your average relaxation time, which is constant. So M upon N E square tau is a constant, okay? And this constant, it depends upon the nature of the material and the temperature. Here L means length of the conductor. Length of the conductor can be varied. A means area of cross-section of the conductor. The area of cross-section of the conductor varies, so L is variable, A is variable, but mass of the electron is constant. Number of electrons per unit volume is constant. Charge of an electron is constant. Average relaxation time is constant. So since this whole quantity is constant, so we can write M upon N E square tau is equal to constant known as rho. In that case, your R will become rho L upon A, where rho is constant and is known as electrical resistivity. So this electrical resistivity, which is given by M upon N E square tau, is constant, okay, and its value depends upon the nature of the material and the temperature of the material. So this resistivity is independent upon the length of the conductor. It is independent, okay, upon the area of cross-section of the conductor. Here your resistance depends upon length of the conductor and area of cross-section of the conductor. But your resistivity is independent of the length and area of cross-section of the conductor. Okay, your resistivity is a constant quantity, and its value depends upon the nature of the material and the temperature of the material. Now, if you are given a long copper wire and a short copper wire, which one will have higher resistivity? What do you say? Look at the formula for resistivity. Resistivity here is independent upon the length of the conductor. It is also independent upon the area of cross-section of the conductor. So for both the long copper wire and the short copper wire, the resistivity remains the same. Okay? But the resistance varies because resistance depends upon the length and area of cross-section of the conductor. Okay. So we'll try to solve a question. A wire of length L has resistance R. This wire is stretched to twice its original length. Find the new resistance. So there is a wire of length L. So this is your wire which has a length L. Okay. Let's say that A be the area of cross-section of this wire, and if R is the resistance of this wire, okay, if R is the resistance of the wire of length L and area of cross-section A, then in that case resistance is given by rho L upon A, which we have seen, okay, a few minutes back, the formula for the resistance of a conductor. Alright, so that is equation number 1. Now this wire is stretched to twice its original length. So you stretch this wire so that the length gets doubled. Okay, so the initial length was L, so you stretch this wire to 2L, to twice of, okay, the wire has been stretched to twice of its original length. Now as you stretch the wire, then its area of cross-section will definitely decrease, but we do not know how much, by how much it decreases. Okay, now if you stretch the wire, if you stretch the wire becomes thinner and thinner. It never becomes thicker, okay? It becomes thinner and thinner, so its area of cross-section will definitely decrease, but we do not know how much. So let A dash be its area of cross-section, okay, after the wire has been stretched. Let A dash be the new area of cross-section after the wire has been stretched to twice its length. Now, according to conservation of volume, okay, the same wire, since the same wire has been stretched, okay, so the volume of the wire remains the same. That is according to the conservation of volume, right? Okay. So, according to the conservation of volume, initial volume of the wire will be equal to the final length of the wire, because the same wire has been stretched. So there is no increase or decrease in volume. Okay. So the initial volume of the conductor will be equal to the final volume of the conductor. Initial volume of the conductor means area of cross-section into length. Final volume of the conductor means area of cross-section into length, 2L. Here L cancels out. So in that case, your A dash will be given by A upon 2. So if you stretch the wire to twice its length, the area of cross-section decreases by half of its original value. Okay? The area of cross-section decreases by half of its original value. Now, if R dash is the new resistance, then according to the formula of resistance, your R dash will be given by rho, okay, length upon the area. So twice of L upon A dash, where your A dash is A upon 2. In that case, your R dash will become rho 4L upon A, which is your equation number 2. Now dividing equation 2 by 1, dividing equation 2 by 1, that we get R dash upon R is equal to, your R dash is rho 4L upon A, and your R is rho L upon A. Rearranging, R dash upon R is equal to rho 4L upon A into A upon rho L. A cancels out, rho L cancels out. So we have R dash is equal to 4 times your R. So if the wire is stretched to twice of its length, then the new resistance becomes 4 times its original resistance. Okay? If you stretch the wire to twice of its length, then the new resistance becomes equal to 4 times its original resistance. So that is the complete answer for the first question. So question number 2. A wire of resistance R is compressed to half of its original length. Find its new resistance. This is a question opposite to the first one. So suppose we have a wire of length L, and area of cross section A. If R is the resistance of this wire, so if R is the resistance of the wire, if R is the resistance of the wire of length L and area A, then the resistance will be given by rho L upon A, where rho is the resistivity of the material, L is the length of the wire, and A is the area of cross-section of the wire. Now, if the wire is compressed to half of its original length, this time the wire is compressed to half of its original length. That means the length of this wire becomes L upon 2. Now we do not know what happens to the area. Definitely if you compress the wire, its area of cross-section will increase, but we do not know by how much. So let A dash be the new cross-sectional area of the wire. Now the same wire has been compressed, so there is no increase or decrease in the volume. That means the original volume of the wire is equal to the final volume of the wire. Volume means area of cross-section into length, and also area of cross-section into length. So L cancels out, so your A dash becomes twice of A. So if you are compressing the wire to half of its length, then its area of cross-section, okay, increases by 2 times of its original area. Now if R dash is the new resistance of the wire, then R dash will be given by rho. Rho is always constant, okay, for the same material at the same temperature, rho always remains, resistivity always remains constant. And L now becomes L upon 2, and area becomes twice of A. So in that case, your R dash will be equal to rho L upon 4A. This is your equation 2. We can make this as equation 1. Then dividing equation 2 by 1. Equation 2 divided by equation 1 gives you R dash upon R is equal to rho L upon 4A divided by rho L upon A. So rearranging, rho L upon 4A is equal to A upon rho L. A cancels out, rho L cancels out. So R dash will be equal to 1 by 4 times R. We have 1 here, so 1 by 4 times R. So if you are compressing the wire to half of its original length, then the new resistance becomes 1/4 of its original resistance. Now there is a very shortcut way to solve this kind of questions. I have solved 2 questions, okay, in the long way to make you understand, okay. Now there is a short way in order to find out the new electrical resistance, okay, if the wire is stretched, compressed, or beaten. Suppose the wire is stretched, compressed, or beaten. Then the new resistance of the wire will be given by N squared times your original resistance, where N is the number of times, the length is stretched, or compressed. Okay. So here N is the number of times the length of the wire is stretched or compressed. In the previous example, in the first question, you stretch the wire to twice of its original length, right? To twice of its original length. Means in that case, your N would be equal to 2. So your new resistance will be 2 square times R, so 4 times R. So if you stretch the wire, okay, twice of its original length, then your new resistance will become 4 times its original resistance. In the second case, you compress the wire to half of its original length. In that case, your N is equal to 1 by 2. You have compressed to half of its original length. Then in that case, your new resistance will be 1 by 2 square times R, N square times R, so 1 by 2 square times R. That implies your R square will be 1 by 4 times R. So using this formula, okay, we can conclude that if the wire is compressed to half of its original length, then the new resistance will be 1/4 of its original resistance. So this is a very important formula. So this is what you have to note.